Well, hello again, it's Cliff here from Down Under. In this video series, I want to go through making the Hallmark ITTP Bodies as an example of medium scale batch production. So it's going to be parts production from small CNC machines like the Tormachs. So I'll start right at the beginning with the raw material and setting it up in the Tormach lathe and machining one end, spinning it around, machining the other end, setting up the tools and discussing all the little tips and tricks along the way. Then the next stage will be setting it up in a little 3-axis mill, machining the top portion or the end portion of the body, setting it up the next. If you like, it's a video book, but a hands-on book. There could be chapters or episodes. The next chapter might be doing the 4th axis machining and so on. So I'll go right from the beginning. Hopefully I'll get as far as the final part. And it'll be a great opportunity to demonstrate different setups, different machining techniques, tips and tricks along the way. And I'll also mention other videos that are relevant so that you can go through and find those in the Thread Express YouTube playlists. Well, before we get down to the nitty-gritty of each chapter or episode, I'll put in a quick montage just giving you an overview of what these videos is about so you can put it in context and see where it's all going and where you have been before if you've watched other episodes, just to bring it all together at the beginning of each video. Cheers. So now we're going to set up and machine the bodies in this small CNC, the Tormach 1100. So we're going to machine here with a 6mm end mill the following features on the bodies. We're going to machine these slots down quite deep, 28mm deep, and then we're going to spot and drill these pogo pin holes right through and these threaded holes down to depth. So there's 3 cutters, the 6mm end mill, the spotting tool and the 2.5 drill. And for the end mill, because it's really deep, I'm just using a standard length aluminium carbide tool, but I'm just grinding an undercut so that it can go down the full 28mm. So I'm going to grind a little bit of an undercut in the shank with a diamond grinding bit, just so that I can get it down 28mm plus a bit of clearance there. And that's a low-cost way of making a long series cutter. And if you don't have diamond grinding, you can buy a long series cutter. It's just a cheaper option for me when I'm doing a lot of production work to stock up on these low-cost cutters. They work really well. Here I'm grinding the undercut of the 6mm standard length end mill that turns it into effectively a long series end mill. Just while I'm thinking of it, have you seen the video on how to dress diamond grinding wheels? I've done a video called D-bit grinders and dressing diamond grinding wheels, something like that. You'll see it in the Thread Express playlists, and I explain a process for really effectively dressing diamond grinding wheels that are worn or glazed, or cheap Chinese ones that really just weren't any good in the first place. And I go through a method that's very effective. It gets your diamond grinding wheels better than new, very accurate and sharp again. So have a look at that video. If you've not got into diamond grinding, you may not want to justify the cost of a D-bit grinder, but it might be worth picking up. In fact, for most people it will be worth picking up a cheap second-hand diamond grinding wheel, or even a Chinese one, although they don't cut as well. You want a good quality diamond grinding wheel if you can afford it, so a second-hand one's a good option, and putting it onto a little bench grinder, and you can do all sorts of work with tungsten carbide with just a basic diamond grinding wheel. I would encourage you to think about that if you're doing advanced work. Well, it's really important to check that your cutter is concentric when it's finally mounted. So there I've got 1/100th of a millimeter dial indicator, and I've got it within 1/2 of a millimeter concentric. Well, that's pretty difficult to achieve. That's pretty accurate, because there's a myriad of things that can be wrong, especially if you've got a TTS system, as I have here. There's a whole host of concentricity potential problems. For example, you've got the main spindle bearings which generate the rotational position. What's the concentricity of the inside of the spindle? That's the R8 taper, that's number one. The R8 TTS collet, inside and outside concentricity, that's number two. Then you've got the actual cutter holder, for example this ER20, concentricity between the shank and the internal taper, that's number three. The concentricity of the nut, that's number four, the collet nut. The concentricity of the collet, that's number five. So you've got 5 different areas that could generate problems due to accuracy issues in those components in the first place, or due to burrs or dirt, or due to a bias. For example, the drawbar can pull the whole assembly off center if it's inaccurate, or the collet nut can bias over the whole assembly if it's not correctly ground on the thread, and so on. So there's a whole host of things that can all input errors, and so it's really worth checking and trying to ascertain where your error is coming from and eliminate it, because if you've got run out in the cutter, not only can you not do accurate work, but you're going to get premature wear on the tooth that's doing all the work, and you're going to get much more problems with chatter and surface finish issues. So it's really worth checking your cutter is concentric. And once you've established that the cutter is concentric, I think it's really important to install the cutter in the spindle each time it's used in the same rotational position. And that's easy enough to do if you get into a habit of, for example, always locking the spindle in a particular place. I've got a little mark there. It can only be in one other position there, so I don't use that one. I've got a reminder. I always lock the spindle in that position, and I always have the cutter holder in the same rotational position by having the engraving always exactly to the front. And so when I check that the cutter is concentric, it's in that position, and each time I replace it, it's in that position. And that way you're going to get much better repeatability. This is really important also for high precision machining. Well, you can see you can get it pretty concentric with all the different diameters with the TTS system if you're careful to check it all and then realign the rotational spindle orientation with the tool holder each time. But if you just put it in randomly, you know, the tool in the collet and the collet in the spindle randomly, I've just done that now, and let's have a look at the concentricity. So we're about 2/100ths short of 0 there. There we're on 0. There we're just, what's that, just on 2/100ths. So that's quite a lot. That's almost a thou run out there. That's going to generate quite a different diameter. And so you can see in my concern in the last video that TTS isn't an ideal system for a tool changer if you want to do high precision work, because you're going to get random rotational position in the spindle and different diameters each time. In addition to that, there's a risk, a very real risk, of every now and again getting a little speck of dirt or chips in under between the TTS flange and the end of the spindle. And I just would be concerned that you couldn't do high precision work part after part for hours on end automatically. It's a good idea to check that your drill is concentric as well. This is very good considering the length of projection for a long skinny drill. It's actually not so critical in this situation because I'm using a centering spotting drill to start the hole. But if you're not using a centering spotting drill, and for example you're using a stub drill straight into the job, then it's very important to check that your stub drill is running concentric. But for any drill, it's a good idea to do this. It's just a good discipline, because you know then that you haven't got a major error, and it's there in the back of your mind that you've ticked that box. Here I'm checking the concentricity of my spotting tool. You can see there that's a D-bit style or engraving style, a D-bit, a D-section cutting tool, and it cuts very smoothly and very well. But it's very important that it's concentric, because the cutting edge has to be the largest diameter. And you need to check that with a dial indicator, that once you get past the cutting edge at that point, it dives away clearance there. Sometimes if it's running out slightly, your largest diameter will be back around from the cutting edge, and it won't cut at all, it'll just rub. Or you'll have so little clearance that it won't cut efficiently. So important to check your spotting tool is concentric. And so another thing is always important to put it back in the same rotational position to ensure that that repeats. Now, checking these tools for concentricity only has to be done once after they're mounted. If you put them back in the same rotational position, you don't need to recheck them each time, obviously. So I'm going to run these 3 tools to make the body internals, and I need to set the tool length offsets now. Oh, it's hard to know how deeply to go into each of these subjects. If I go into it in too much detail, it'll get too long-winded and not be the subject you're interested in. But if I skim over it, I'm going to miss some key points. Okay, well, what I tend to use is a mechanical tool setup for setting the tool length offsets. And you can buy these little units very cheaply on eBay or AliExpress. And they're brilliant because they're a dial indicator type that has a plunger that is set at the same level as those little buttons on either side. And you can put a parallel over the top and set your dial on 0. And so when the tool comes down to that depth of engagement with the dial indicator plunger, you're on 0, and that's a surface that you can probe and measure. So it's very quick and easy to set your tool lengths with a mechanical tool setter. But this particular mechanical tool setter, while it's good value and very compact, it's not that repeatable. It shifts by a thou or two between uses, and so in the end I went ahead and made my own more accurate tool setter using a dial indicator with a pad mounted directly onto it. If you're interested in making one of these, I've produced a video, new design tool length setter. Have a look in a recent video or in my playlists page and you'll find that video. Could be a good little project for you to make a more accurate mechanical tool setter. So I'll just show you that in operation now and show you how quick and easy it is to use this type of tool setter. So the design of this tool setter is the same. Instead of having little buttons, there's this ground surface on either side, and you set your dial indicator to be 0 on that surface, which is your reference plane. Then you can plug in your probe, touch off on that surface with tool 99 in the tool table, Now that we've established that as our reference surface with the probe, we can put our tools in and set the tool lengths very quickly and easily. So we install the tool and clamp it up, and the advantage of doing it on the machine is that this includes all the different clamping and setting errors, and I've shown that in other videos that it's very different from measuring it off the machine because you have errors in drawbar tension, compressing the spindle and the TTS flange and so on. Okay, so now we just come down to that reference surface, and that's designated by this 0 there, and at that point we just hit a button on the tool length setting page and it loads it automatically into the tool table. Well, let's just show that on the setting the tool length page. So we enter the tool number, we're going to call that tool number 124. That brings it up here on the page automatically, and we just touch this button when the tool is on 0 with that dial indicator manual setter. See there, the Z length is 0 on 124. When I touch Z, now we have the tool length installed, 79.933, as quick as that. So for most of you users, a manual tool length setter like this is all you really need. I know some of you will be thinking, no, you need an automatic tool setter, you need an ETS, and there are certain users that will benefit from having an ETS. But I don't want to get into that in this video, it'll just be too long-winded. But if you're interested, have a look at my recent video or in the playlist, find a video, which tool setter, and I go into the pros and cons of the different tool length setters. If you're doing manual tool changes, it's a good idea to make it really bulletproof, so that idiot-proof, so that you can't make a mistake, or much less easy to make a mistake. So I'm working from this end, and when the program calls for tool 24, it comes out of that slot, and it's 2729. That's just a bit of plastic that's like a wipe-out board. You can wipe it off with a bit of alcohol each time you do a job. And it just makes it much safer towards the end of the day when you're getting tired, or you run down to the workshop halfway through dinner, you pop a tool in and you run away again, and you're not really concentrating and you put the wrong tool in. That's a big crunch up, and so this is less likely to happen if you make it idiot proof. So tool 27 is that spotting or chamfering tool. I use it for both spotting and chamfering. It's a D-bit shape, really handy because you can do multiple machining operations with it. So you can see there it's chamfered and spotted ready for drilling on the outside diameters, the locating spigots, and around the profile there. So that looks good. Now we can put the drill in and test that part of it. While it's running, doing the drilling part of the program now, a few little tips and tricks. So down there you can see a spout that takes the coolant out and away from running onto the slideways. You don't want the coolant running on the slideways because it's carrying little particles of abrasive metal and so on, and it's not good. It's going to wash the whey oil off the slideways, and so it's better to have it spouting out away from the slideways. Down here I've got a microfiber cloth, just sort of a bit like a bypass filter. It's slowly cleaning the cutting oil. Just a couple of 20-litre plastic bottles that I use, mounted in a plywood coolant box that I can wheel around on coasters. Oh, the same on this one, but this is a Mark II version. If you're interested in these designs, have a look on my website playlist. You'll see information on these types of things also. Alright, well, thanks for watching that episode or chapter. Hopefully you found something useful in there. And if you did, please like and subscribe. That helps with the YouTube algorithms, as you probably know, which brings it out there to more and more viewers. Please stay with me, and I will be editing and completing the next chapter or video and publishing it soon. Thanks for watching. Cheers. Throughout the course of this video series, I'll mention different videos that I've made on specific subjects, and to help you to find those, if you go to the Thread Express public homepage, you should see a page like this. Most of you will be familiar with this, but if you click on the playlists here, then you'll see all the different subjects split into categories. For example, you might be interested in spindle tapers, R8 versus TTS and so on, versus BT30, or whatever subject. Just go to the playlists, find the group of videos grinding related. You'll see there's a whole lot of videos on, for example, dressing your D-bit grinder diamond wheels. So just refer to it that way. Will be the quickest way to do it. There's several hundred videos there altogether.